All right. So last time, of course, we were talking about static arrays. And, I mean, static arrays, they were similar to lists. We were using lists in Python. They were similar in the sense that it lets you hold on to kind of like a series of information, like this like linear series of information. Can someone do me a favor and close that door? But unlike a list, the arrays had like a fixed size. Also, unlike the lists in Python, everything had to be like the same type in the arrays. What else did we notice? With the static arrays, before you hit run, like before you compile your code, you have to somehow know how big your array needs to be. So there's a bunch of limitations. Was there anything else that you remember that I didn't say? I can't think of any, but there are a bunch of limitations compared to the lists. Now, be aware that lists and arrays are really very different things inside the computer. The lists are a more general, higher level data structure. In fact, later on in this course, we're going to build lists. And we're going to build them two different ways, and we're going to compare them. One of the ways we can build a list is with an array. So we'll see that. But they are different despite their similarities. Now we're going to talk about dynamic arrays, which are you get a little bit more freedom with them. So, we're going to learn a little bit about static and dynamic memory. We're going to learn about dynamic arrays and learn about how awesome dynamic arrays are, and we're also going to learn how annoying they are too. So, just a little bit on memory. This is by no means exhaustive, okay? In fact, this is going to be deliberately high level, just so I can give you an idea of what's going on. So variables we've made, whether it's a regular old variable or an array, like a static array, we know them at like compile time. So when I create a variable called like int my integer, it doesn't really matter what value's inside of it right now. The value that's inside that variable can change throughout runtime. But the fact that that variable exists and the computer knew to go set aside this much RAM for that variable, it needed to know that before we hit run. Same with the static arrays. It needs to know how big it is. How many slots are there? We can change what we put in the slots at runtime, but it needs to know how big it is before we even hit run. So the computer knows to go create a chunk of RAM to put and set up for that stuff. So this is an example like this. In this example, okay, I'll go set aside a chunk of RAM for a single integer here. I'll put 10 in it, of course it could change. Here for a double, here for an array. A contiguous chunk of RAM for 10 integers. No problem, I'm going to go find room for it. And the computer's really happy about this. C++ is really happy. But of course, if you look at this code, you might really want to be able to do this. This seems reasonable, something that you might want to do. What if I don't know how big it is? What if I don't know how many inputs I'm going to read from the user? What if I don't know what I'm going to read from a file? You don't know how big that array is going to be. It might seem reasonable. Why can't I ask the user, tell me how big to make the array? 7? Okay, I'm going to go make an array of size 7. Great. Why can't we do that? It seems that we should be able to do that. And we can't do that with static arrays. It's against the rule. It makes sense, but it's not allowed. Remember, we had a really easy workaround for something like this. If I knew that the amount of input the user's going to give me is going to be no more than 100, well, I could simply make an array of size 100 and then do something kind of like this, say, well, how many things are you going to give me? And then if they say 7, you only take the first 7, but you've got all that extra RAM that you could put more stuff in, but you're not going to use. So there's a workaround. You might argue it's a little bit wasteful, but we got a lot of RAM these days. Now note, again, we're 100% allowed to change the contents of these variables at runtime, but not the fact that they were created and put somewhere in RAM. Like we created a box to put something inside of it. I put an asterisk there because there's always a million and one exceptions, but whatever. Yes?
You were saying that you can't do that for static arrays, but you can ask the user when you can for dynamic.
Well, I haven't even told you about dynamic arrays yet.
Oh, okay.
So you cannot do this with static arrays. Spoiler, we'll be able to figure out a way to do it with dynamic arrays, but it's a little bit different. So yeah, we're allowed to change the contents of these variables. We're just not allowed to start allocating different amounts of memory during runtime. Or can we? So here's a little bit about memory. So we've got like the static memory. The computer sets this up when our program starts. Like before that first line of code even starts running, it's going to kind of set all the stuff that it needs to know. It's going to create those variables that you said. Then there's stack memory. These are things that are allocated during runtime, but C++ is kind of managing that for you. So for example, you'll, I think, do I have the example here? Yeah, so for example, variables inside the function, right? You've got a function and maybe inside that function we've got like 2 variables. Well, when that function gets called, it'll kind of like dynamically create those variables for you, but as soon as that function's done, it deletes them for you. So these are things that the computer, like it's in the code, it's kind of prepped for it, it's all happy. But now we've got the dynamic memory. We can allocate and deallocate RAM to our heart's content. We can do this forever, which is awesome, but it's kind of like the Wild West. And technically, memory is a limited resource, so we might actually never get the RAM allocated that we wanted because there could be a problem. Like if your computer only has this much RAM, but you ask for this much, well, it's obviously not going to work. Now, don't worry, in practice, this is not going to be a big deal for 162. And you probably won't have this issue come up unless you're deliberately trying to. But long story short, we can actually have an array that has a size not known at runtime, or not known until runtime, pardon me. And here's how we would do it. You create an integer pointer. And then you say something like this, equals new int some value, where some value can be different every time you hit run. Maybe that was read in, and the user submitted like 7, and then the next time they hit run, they put 77. This will work. Notice though, that on the left side, like int star a, where before with the static arrays, I would use those like square brackets. And I also showed you that you could use the pointers as well, but the convention really was more along the lines of square brackets when declaring it. It's just going to be a pointer for the dynamic stuff. And what else here looks new that you haven't seen before? New. Well done. New. Now the right-hand side looks kind of, I mean, you see the square brackets, but it's used differently. Before, when you wanted to create something of a size, you would put the square brackets next to the name that you were giving it and put the size. Now it's on the right-hand side next to this new keyword and whatnot. So new. It's a special operator that it like says to the computer, okay, here's what you're going to do. And listen up, this is important. Because if you know what it's doing, high level, you won't like, you'll be a much happier person because things will just click a little bit more. When you say new, what it's saying to the computer, okay, go create, so the int, open bracket, variable, whatever. What it's saying at runtime, some value, somebody yell out an integer. 5, okay. I'm going to go create a chunk of RAM. I'm going to go find a chunk of RAM in the dynamic memory over here. And it's going to be 5 big. Okay? But what the new means is like go create it and then return the memory address of where it starts. So it's actually giving us back the memory address. And then when you look at this code, where am I storing that memory address? The pointer variable A. Everyone gave me variations of it, but I like your variation the best. The integer pointer A. Because it's just going to point to the very first location of wherever that was allocated, right? Cool. So, sure, it's a pointer, but don't worry, we can still use the square bracket notation, and I do highly recommend you do that. Although you could do all that pointer arithmetic, don't. So you can still do something like this. Just like that there. Here I'm doing it all in one line of code, doesn't really matter. And then I've got that for loop. Look at this code, what is this code doing? Have a look, don't yell at the answer, just give yourself 15 seconds. You should be able to figure out what this is doing. Who's brave enough to say it out loud? Do someone different. Come on, someone's got to do it. What do you say?
It's counting, it's making an array from 0 to some value.
Yeah, that's what it's doing, but then what are we doing inside that loop?
Taking, counting I from 0 to some value, and the index is the array index I, and then you add I.
Yeah, so all we're doing is we're saying, okay, if the array is, like if some value is 10, it's going to create an array of size 10, a dynamic array of size 10, and then index 0, what value is going to go inside of it? 0. Then index 1, what value are we putting inside there? 1, and so on. Why? Because that's what I wrote. That's all. If you really like, you can do the pointer arithmetic, but don't. So why not always use dynamic arrays then? Well, okay, yeah, sure, fine. But there are some catches, right? Technically, you might run out of RAM, but that probably isn't going to be an issue. There's some extra overhead associated with it, and things get kind of confusing when you're first starting out. By the end of the semester, you're not going to be confused. You're going to be a whiz. But it can kind of get a little hairy. Don't worry too much about that. If I do something like this, what is this doing? Take your time based on what I just said. Think about it in your head. What's happening? I'm going to draw it. We're just going to follow the rules. And think, you have your hypothesis in your head, and we're going to see if you're right or wrong. So what am I doing? Well, I'm creating an integer pointer variable called a. Okay, that's the first line there. So I've got a. It's going to be a pointer to an integer. Then what's that next line say? Oh, it's saying go over to somewhere in dynamic RAM and create an integer array, right? It's over here. I drew my array as this giant blob. Don't worry about it. And then, of course, we're getting back the memory address of where it is, which gets assigned to A, so I'm just going to draw it as this. We're done the second line of code. So far, so good. Any questions at all? Now's the time to ask. Yes?
It's some value predetermined.
It wouldn't be predetermined. Maybe like the line right, depends on what you mean by predetermined. If it's at compile time, it doesn't have to be. If it's at runtime, you can imagine like right before declaring this, I asked the user, give me a value. And then they entered something and then I put it into the variable some value. So if you hit 7 and you hit enter, some value is going to be 7. If you had put in 152, it's going to be 152 next time. It doesn't really matter. It's just a variable, yeah. And that variable can be different every time you hit run. It doesn't have to be fixed like with the static arrays. And this really is the crux of why these are handy, because they can be whatever size we want. Good question. Anything else? Okay, so what does the next line of code say? All right, so, just go create an integer array somewhere else in RAM. Oh, maybe it's over here. Right? Oh, and give us, get the pointer to that and put it into A. All right, no big deal. So we're overriding what's in A, right? Just replace it. Assuming it starts here. So this is what happened. Does this make sense? Any questions at all?
At the very beginning, you said that you're allocating space in dynamic RAM. When we're talking about RAM in general, they're like specifically predetermined, like static RAM.
Yeah, the computer will have it like, okay, this is what I'm using that's, yes. Also note that this part here, that A, the variable for the integer pointer is in static RAM. This would be in dynamic and that would be in dynamic. When you see new, think dynamic.
So they work together.
Yeah, oh yeah, absolutely. So what observation do you see here? If it might seem kind of obvious to you, that's fine. Like it might be obvious. So don't be afraid to suggest something that you think might be silly. What do you see? Not much happened, but what do you see here? Raise your hand. If I see your people mumbling, I want to see if we get somebody else. Yeah?
The second one becomes pointless in this situation.
The second one, like this one becomes pointless, you mean? Yeah, kind of like, it's gone. But we got a problem. We told C++ to go create and allocate this chunk of RAM. And as far as C++ is concerned, this chunk of RAM is important. However, do I know how to get there anymore? It's gone. I did know. I saved its memory address in here, but then I overwrote it. So it's gone. It is now impossible for me to go find this. Unless maybe I start searching through all the RAM or something, but that's going to be problematic. So I can never get back there. In other programming languages, like Python, we had something called garbage collection, where there was some process running that would go look for scenarios where there's a piece of RAM allocated that is never referenced anymore, so we have no way to get back to it. And if it ever found that, it would just delete this for us, because, well, you just don't need it anymore. It's gone. If you don't know where it is, you can never get there, so it's useless. So it would delete it for you. C++ isn't going to do that. In this situation, we've created a big problem. Does anyone know what we call this type of problem?
A memory leak?
Who said that? A memory leak. This is exactly a memory leak. What this means is the computer created this chunk of RAM. Maybe it was gigantic. Maybe this was an array that was like a bajillion indices long. And it took up like 2 gigs of RAM. Something crazy. And then you just lose reference to it. But the computer's like, well, yeah, but this program that you're running is using up this RAM, so I can't mess with it. Do you think that's a good thing or a bad thing? It's a pretty bad thing. Now you might say, I've got lots of RAM, no big deal. No, you're bad. Don't think that. These are dangerous. But don't worry. There's a simple way to address this. Yeah, I've already explained it, so that's bad. All you have to do is delete it. That's it. That's all you got to do. So in this scenario, this is what I should have wrote. I should have said, okay, A is this new thing. Delete the thing that A points to. Remember, you're not deleting A, you're deleting the thing that A points to. Very important note. So in this situation, I would have erased this first. Then reassigned it. Don't reassign and try to delete because it won't know what it's trying to. It needs to have reference to the thing you're deleting. Yeah?
So if you're, so after you run the sentence, if you don't do the delete thing, after you run it, and it creates both different places, when you stop running it again and then you go messing around with the code, is that RAM freed up?
Yeah, so every time the program finishes, it will free it up.
Okay.
But imagine I just put this in a loop and didn't delete and it kept reassigning. and I let it run for a day, the RAM's just going to go, we're going to have a bad situation. It's really bad. So you don't have to worry about breaking your computer or anything. But, yeah. This was, I mean, it still is a big deal, don't get me wrong, but like a number of years ago, back in, let's say, the 90s, when the amount of RAM we had was, when there wasn't a lot of RAM, but programming was becoming more and more accessible, people were writing programs, shareware, you know, all that type of stuff. Memory leaks were an issue because you'd have software that had these leaks and it would just kind of like blow up while your computer's running. Problematic. But whenever you're done with dynamically allocated RAM, just delete it. That's it. It's easy. Yeah?
After the program stops running, does it still save that in the RAM? Or
No, it'll delete it. In fact, imagine that this, like after that last line of code, that was the end of my main. That was literally the last line of code of my program. You might say, but then that new thing that A's pointing to, like over here, you never deleted it. One, I should have, but it doesn't really matter because it'll get freed up after it's done. But if you turn this in on an assignment type thing, you would lose a mark because you should delete after, for sure, okay? If you're using Visual Studio, I'll give you a trick to kind of search for memory leaks as well. There's probably a way to do it on Macs too, I just don't know offhand. But yeah, you gotta delete. And if you're thinking, how am I ever gonna remember? Yeah. If we're deleting an array, you have to have the square brackets. You could do something like this. This is 100% valid. What is my int pointer? An integer pointer. And I see new int. This might look weird, but what do you think I just created? Based on all the rules we saw, who's brave enough to take a guess? You could be wrong, don't worry about it. I'm putting you on the spot.
Size 5 array.
Nope, it's not going to be an array, but good guess. Who said that though? An int that's 5. Who said that? Where? There. An int that's 5. But where is it going to be stored? I just heard a in dynamic memory. Let me ask you this. How many integer variables did I create? None. I created a chunk of RAM that assigned an integer to it somewhere in dynamic memory, but the only variable that I created was an integer pointer. It's interesting, right? And that integer pointer is pointing to a chunk of dynamically allocated RAM that has the integer 5 inside of it. But that's fine. So I could do this. I mean, I'm going to have to dereference the pointer, of course, print it out. Why would we want to do this? Well, at this stage, it's going to seem rather silly, but we will use it eventually, because what if we don't have an integer variable to put something in, but we need to store an integer variable? Well, we'll get there. Yeah, okay. But of course, when we're done, we must do this. Delete. But notice that this delete didn't have the square brackets. We don't need it because it's not an array. We're just deleting a single thing. So yeah, just like with the dynamically allocated array, we must delete the int from RAM. Yeah?
Would doing that use less memory than pointing to a variable?
No, it's going to use the same. It's still just going to be the same chunks. I mean, there might be a very specific engineering question where it's well, based on how C++ works, this, that, and the other. But from a purely computer science perspective, no. There might be some weird things that the compiler's doing that I just don't know about. I'm not a C++ whiz, so maybe, but really, you wouldn't expect it to be. Because at the end of the day, it's still going to be the same amount of RAM being allocated for things. Just where was it? Dynamic or static? Yeah. Other questions? I like this. Keep going. You had half a question back there.
I'm just trying to figure out, are all pointers dynamic?
So, no, not necessarily. Pointers are just going to be pointing to another piece of RAM. That piece of RAM it could be pointing to might be in the static part or in the dynamic part. Doesn't really matter. The pointer is it's just an integer pointer. It's a box in RAM that holds on to a memory address of another place of RAM that should have an integer inside of it. You're going to have to take your time when playing around this. It takes a little while to get used to the integers, integer pointers. Is this a pointer? Is this the thing? Do I want to dereference? Is this the memory address? But don't worry too much because chances are you'll, just with practice, it'll come together pretty quickly. Just whenever you create the variable, whenever you're passing the variable, whenever you're writing the function, think to yourself, do I want to pass the value or do I want to pass the reference to this thing? Just take your time, just think about the types. Don't rush, take your time, you'll be in great shape. Yeah, we don't need the square brackets. Great. So you're thinking, how am I going to remember? Do I have to delete this? Do I not need to delete this? This, that, and the other? Here's the rule of thumb. Just delete things that you don't need anymore. When you don't need the thing anymore, delete it. But how do you know when to delete it? Well, we're deleting the things, not the variable. So if we've got this integer pointer and I say delete A, it's not deleting this. What is it deleting? Good. The thing it points to. Exactly. So here's the simple rule. For every new, we need a delete. For every variable that you create with a new, you're going to want to delete it. For every variable that we create a new with as an array, we're going to need delete with the square brackets. That's the rule. Yeah?
So for assignments and stuff, would you be fine with just a bunch of deletes on the last few lines of code? Or do you want it closer to where it's actually used?
It really depends. It would be better to free it up as soon as you don't need it anymore. But do hold on, if you need to delete it at the end, that's fine. But it's good to delete as soon as you don't need it anymore. And as we go throughout the semester, and I start showing you examples of the fancy data structures we're going to use, you're going to see examples of where would be a good idea to delete it. And I'm willing to bet it'll make perfect sense to you as we go, because I'm going to make sure that we explain the intuition and why we're doing this there. And it should all make perfect sense. And as soon as you get more familiar and you see more examples, it's going to be nice, clean, come together. So making use of it. Can you see this at the back? It's a little small. Well, it's the best I can do today. What does this piece of code say? Take a second. Can you see it at all? Because I can copy and paste it into Visual Studio and zoom in. Would that be better? Be honest. Someone at the back say. You can see it? It's not that bad. All right. Well, maybe for future I'll make sure it doesn't get too small. But take a second. Look at this code. What's it doing? Give yourself 20 seconds. Make sure it makes sense. Who wants to tell me what it is? Someone raise their hand. Yeah.
Making an array of the size.
Well, but where do I get size from?
Well, you asked the person to put numbers.
Exactly. We say, okay, tell me a size. You give me a size, then I go create a dynamically allocated array somewhere in RAM based on the size they gave me. Exactly. Now what does this do? If you read the comment, it should make perfect sense. What am I doing? All I'm doing is going to each index, and then putting the square of whatever index it is in it. So 0 is going to be 0, 1 is going to be 1, 2 is going to be 4, 3 is going to be 9, and so on. Why is it squared? Well, I'm just multiplying the index by itself. That's how you square something. Or the integer by itself. Then what is this doing? Of course, it prints out the contents of the array. How do I know? Well, all it's doing is saying for int I 0, well, I is less than the size of that array, I plus plus. Then we're saying, okay, print out array at I every time through the loop. Of course, we're putting an endl after all of those, so there's going to be, it's all going to be on a different line if it were to be run. Then of course, if this is the end of my main, what should I have here? Assuming, yeah, like this is it. This is like the last line of code I really wanted to run. What am I missing? Delete. Why? How do I know? Well, I got that new. So I'm going to need to put delete with the square brackets and array. There we go. Yes?
I thought we only delete if we're allocating it to a new address in RAM.
So we would absolutely want to do it then, but really, you kind of got it backwards. Your head's in the right place. In that situation where I changed it, we wanted to delete it first. But really, we're not deleting it because we're making it point somewhere else. We're deleting it as soon as we don't need it anymore. So presumably, I didn't need this anymore, so I should have deleted it. Oh, and then I just happened to reassign it. So it's not because I wanted to reassign it. It's because I didn't need it anymore, which, because I wanted to reassign it, caused it that I didn't need anymore. But that's the catch. Good question though, because that is a funny thing.
But then shouldn't we delete every variable that we're done with?
Yep, and I should, when this program's done, I should say delete A again. But only the things that were dynamically allocated, the trick there is look for the news. So because there's a new in here, like size, the int size, I don't need to delete that. Because it was in static memory, and C++, it'll figure out getting rid of static memory when it's done. It's fine with that. It'll delete it for you. But the stuff in dynamic RAM, the stuff in dynamic memory, you are in control of. And how do you know? Just look for that new. That's the rule. So int size, it's fine. That's static. New int size, that's dynamically allocated, so I had to delete it. Yep.
If you were like squaring something or like multiplying it by itself, or like in C++, is there like the I star star if you wanted to do that?
Like if you wanted to say like
Multiply
5 star star 7, like that would mean 2 to the power 7.
Oh,
Is that what you were asking?
I mean as in like the same way plus plus.
Oh yeah, you could say, I'm sure there's combinations of that. Yeah, I just don't know offhand. It's probably like star equals and then whatever you want to multiply it by. Yeah. Try it. Try it with just star star. Tell me what happens. If you're wondering what's the power operator, so remember in Python, if you wanted to like square something, you would say my number star star 2. Or if star star is kind of like to the power of. You don't get that for free in C++. You need to do some like fancy imports and whatnot. It's probably in the math. You'll figure it out. Other questions? So what if the computer won't allocate enough RAM? It is possible that we ask the computer to allocate RAM that it just can't. Maybe there's not enough room, or who knows. This is very unlikely to happen in 162, so don't worry. Unless you're deliberately trying to do it, you're probably going to be fine. But there are, and I'm not 100% sure if this is true, like this might just be a Visual C++, so this might just be a Microsoft thing, but it will throw an exception saying like, oh, bad allocation exception. So you might kind of remember that like try except thing in Python. We can do that here, like, oh, try to allocate memory, and if it doesn't work, here's what you're going to do. We're going to talk more about exceptions in C++ later in the semester, so don't worry too much. And this exception, I'm not sure if it exists in just regular old C++. It might only be on like Microsoft, so I don't know about the Mac people. Long story short, you probably will never look at this again for the rest of 162. I'm just FYI. Any last questions about dynamic arrays? So let's look at a quick example of showing you the difference between static and dynamic. Can you see at the back decently? Awesome. Is that even better? Fantastic. So let's create a static array. What do I type? Well, let's put integers in it. Int. And I'm going to say my array. There we go. And how big do we want it? What? 10. Sure. Great. And let's say, what do I want to do? Let's do like 4 int I equals 0. I is less than 10. I plus plus. And what do we want to say? My array at location I equals 0. Just because. Right? Let's just set everything to 0 because that's a good thing to do. Then down here, what am I going to do? I'm going to say my array. My array at location 1 equals 10, and my array. What? Come on. At location 2 equals 20. What's it upset about? Well, let's see if it shuts up once it gets running. Oh, and you know what? I'm going to make a function up here. It's going to be void. Now, a lot of people were asking me what the heck void meant. I'll just reiterate. All functions you write in C++, the first thing, like in front, like I put void, see how there's int in front of main? That means that that function must return something of that type. But what if you have a function that you don't want to actually return anything? Well, then you put the type as void to mean just ignore. Yeah?
So why is the main function an int?
Why? So it just goes back. So 2 things I want to hit here. What you would do is you have exit codes. So if I'm running, like I'm on Windows and I'm about to run my executable for the program I'm about to write, it's going to run, it calls the main function. And when the main function's done, it's going to return like that exit code. And by convention, exit code 0 means everything's good. But you can imagine where it's like, let's say, for example, I tried to allocate RAM. Try to allocate this RAM. But if it couldn't and it returned that exception, I will be like, okay, except, although in C++ we call it catch the exception. So catch that exception, and if you do, just stop running but return exit code 1, which to me means, oh, there was a memory allocation issue. So that's why main will return an int. It's like an exit code to mean something to the user. Now you might ask, you just said all functions that have that return type must return something. Did I write return an integer at the end? I did not. This is C++ will do you very few favors in life, but one of the favors it will do is if you don't write return 0 at the end of your main, it'll just kind of like do it for you before it builds the project. Really, I should have that, and now it's fine. So let's go up here. Void, print array, int pointer, to print, and int n, where n is going to be how many things I need to print out. Because remember, if I want to go through a for loop through that array, I can't just ask the boring old array, hey, how big are you? I can't do that. That's not a thing. So this function's going to need to get a variable to say how long it is. So the programmer's going to have to make sure that that information is moved around. print allocation I. There. So what does this function do? Well, it's going to look similar to the code that we saw in that one slide that just says go through the array and print everything out. Right? Cool. So if I go down here and say print array, and I'm going to give it my array and 10 because that's how many things there are. Let's build it. Now I still haven't increased the size of the font in the console, so for those of you at the back, oh, what did I do wrong? Oh, I guess I have to rebuild. There. 0, 10, 20, 0, 0, 0, 0, whatever. Cool. But of course, this is a static array. Let's see what happens if I do something like this. Cool. All right, I don't know what's going on with Visual Studio. I don't know if it's trying to be helpful, but it's annoying. Array size. Oh. So you can already see Visual Studio is getting mad at me, right? And this says expression must have a constant value. I can't do this. It's a static array. Now, I know you all know by looking at this code that array size is 10 and it doesn't change. So it is like a constant value, but C++ doesn't trust you. So it's saying, nope, nope, can't do this. You can't. You can, one sec, you can, if you do, that'll shut it up. Because you're saying, okay, it's a variable, I know, but it's constant, so no one's ever going to change it, and it can't get changed because C++ won't let you change the constant, and now it's fine. You had a question? Or was that your question?
Yeah.
Okay, cool. Now, of course, we want to try the dynamic arrays. So all I'm going to do is I'm going to turn this into that, right? And then say equals new int of size and then down here I need to be good and say delete the thing my array points to, rebuild. Probably going to fail the first time because I think there's something funny with the project. Oh no, it worked. And it still works just fine. But the difference, first of all, look how easy it was for me to change it. It really wasn't that hard. I just went in, I added the delete, but really all I did was change this to an integer pointer instead of that array notation and put the new over here. But all the other stuff was left alone. It's pretty neat. Everything else just kind of worked the same with the data structure. It's a linear data structure. It worked the same, even though I changed it from a static to a dynamic. Isn't that neat? Cool. Any last questions about that? Yes?
Would you be able to delete the array inside the user-defined function?
You mean up here?
Yeah.
Sure. Let's see what happens. Something's wrong with my project. For some reason, I have to like build twice. I don't know. It's all good. All that matters is that I'm deleting that thing that was dynamically allocated with some pointer. But notice I didn't do it with the pointer my array. I did it with this pointer, which is a different variable. That gets me to the exact same piece of RAM, but neat nonetheless. Yeah? Yeah.
And it builds successfully in the program.
There you go. I guess it's just Visual Studio being extra picky then.
Okay.
Cool. So I guess that's not a C++ thing, but it's a Visual C++ thing.